Hello everyone, here is a tricky question from Ionic Equilibrium. The solubility of AgCN in a buffer solution of pH equal to 3 is X. In that case, what is the value of X? Assume that no cyano complex is formed. What they mean by cyano complex is dicyano argentate 1 complex, that is AgCN twice, that is not forming. That is the assumption that we have to make. Many students think that this question is related to common ion effect, but it is not. There is no common ion effect here. This question is related to simultaneous equilibrium. You see, we are in the acidic buffer here. Imagine two scenarios. Let us say pure water is one scenario, and then acidic buffer, that is the another scenario. pH value 3. AgCN would dissociate as Ag plus Cn minus, but when we are in the acidic buffer medium, AgCN would still dissociate as Ag plus Cn minus, but we do have H plus ions because we are in the acidic buffer. What that will do? That will react with this, isn't it? So therefore, we would have Ag plus ions plus Cn minus ions plus HCN, which means we need to take care of the concentration of these 3 ions. That is the issue here. So once you understand this, then it is easy to solve this problem. Now the Ksp value is given and also the dissociation constant value is given. HCN, if it dissociates, it would dissociate as H plus ions and Cn minus ions. Therefore, Ka is equal to concentration of H plus times concentration of Cn minus divided by concentration of HCN, which is equal to 6.2 times 10 to the power minus 10. This value is given. So therefore, we can write that Cn minus plus H plus giving HCN. For that we can write that K is equal to 1 by Ka, isn't it? Now let us establish the concentration relationships, that is the mass balance. Every mole of AgCN dissolves produces 1 mole of Ag plus ions, isn't it? AgCN, every 1 mole would give Ag plus ions. So therefore, it would also give Cn minus. So therefore, concentration of Ag plus ions is equal to X. Now the dissolved cyanide exists in 2 forms. This is not in free form. So therefore, we cannot simply write X is equal to Cn minus in this case, isn't it? There is something else. We have to add the HCN concentration also. So therefore, X is equal to Cn minus plus HCN, isn't it? So therefore, let us use the Ka expression to relate Cn minus and HCN, which means concentration of HCN is equal to H plus ion concentration times Cn minus divided by Ka, and we know that pH is equal to 3. We also know that pH is equal to negative logarithm of H plus ion concentration. So therefore, H plus ion concentration in this case has to be 10 to the power minus 3, isn't it? Otherwise we can't get the pH value 3. So therefore, concentration of HCN is equal to 10 to the power minus 3 times concentration of Cn minus divided by 6.2 times 10 to the power minus 10. So, this would become 10 to the power minus 7. Therefore, we can write that this is concentration of Cn minus, that is 1 times concentration of Cn minus divided by 62 times 10 to the power minus 8. So, let us figure out 1 by 62. 1 by 62 we can't divide, so put a 0 and raise it to the decimal. We still can't divide, so put another 0 and now we can do it one time. So, 62 remaining 38, we can't divide, put a 0. Now, we can do it 6 times. If we do it 6 times, then it is 372 remaining 8, add a 0, we can do it 1 times 62. So, we would stop at this stage. So, this is 0.0161 times 10 to the power 8, is not it? So, therefore, concentration of HCN is equal to 1.61 times 10 to the power 6 times concentration of Cn minus. Now, let us substitute the expression for HCN back into our solubility equation, that is X is equal to Cn minus plus 1.61 times 10 to the power 6 times concentration of Cn minus. So, therefore, this is equal to Cn minus times 1 plus 1.61 times 10 to the power 6. This value is overwhelmingly larger than 1. So, therefore, we can ignore the 1, is not it? Therefore, X is equal to 1.61 times 10 to the power 6 times concentration of Cn minus. So, therefore, concentration of Cn minus is equal to X divided by 1.61 times 10 to the power 6, and Ksp is given as concentration of Ag plus times concentration of Cn minus. So, therefore, 2.2 times 10 to the power minus 16 is equal to X times X by 1.61 times 10 to the power 6. Therefore, X square is equal to 2.2 times 10 to the power minus 16 times 1.61 times 10 to the power 6. So, therefore, this will become 10 to the power minus 10 and 161 times 22. So, that is 2, 6 times 2, 2 remaining 1, 2 plus 1 3. So, 2, 2, 3. So, 2, 4, 5, 3. So, 3.542. Therefore, X square is equal to 3.542 times 10 to the power minus 10. Therefore, X is equal to square root of 3.542 times 10 to the power minus 10. Therefore, X is equal to 1.88 times 10 to the power minus 5 mole per liter, which we can approximately write it as 1.9 times 10 to the power minus 5. That is the correct value. This means compared to the pure water, the solubility of AgCN, if it is pure water, it would be simply square root of Ksp, isn't it? So, in that case, we would get a value of 1.48 times 10 to the power minus 8 mole per liter. On the contrary, here we are getting 1.88 times 10 to the power minus 5. That means, in the buffer, it is 1000 times more soluble, isn't it? Compared to pure water, this is in pure water. In buffer, this is 1000 times more soluble. This is in acidic buffer, this is pure water. So, that is what we need to understand here. Okay. Therefore, option 1 is correct. This is a tricky question for sure, but if the examiners have decided to make the paper tough, then they can ask these kind of questions for sure.